on it. Yeah. Thank you. Hooray. How do you get the attention when the person who needs to switch the microphone on is the furthest away? Okay, good morning. Welcome back to the first of the parallel sessions this morning. If you could follow the standard instructions of please turn mobile phones and laptops and things to silent, so not too many bleeps. First speaker in this session on not how networks can be used, but how networks can be misused and what to do about it, is Merika Kao from Double Shot Security in Seattle, and also various other points around the globe. I was quite tiring reading her bio as to where all she's spoken, who's talking about network level defense.
Hi there. So, I don't know, I got to get used to this podium here. So the talk will be about network level defense and basically what are people doing currently to defend their networks and how are things changing with peer-to-peer networks and IPv6 coming down the pipe. Out of curiosity, how many of you are working, playing, practicing with IPv6 today? Cool. How many of you are using IPsec? Okay, not unusual. So I will tell you right away, I'm an IPsec bigot. I think it's very much an underutilized technology, but there's work to be done in the industry to actually make it ubiquitously usable. So the agenda will be, I'll first talk a little bit about risk mitigation versus operational efficiency. I think we basically mostly all know about these issues, so I won't spend too much time on them. Required network security measures. It never ceases to amaze me that the same issues keep propping up all the time, like route hijacking. The last one was with YouTube, right? And a lot of these simple issues really can be, well, I shouldn't say simple, but a lot of these widely publicized attacks can usually be mitigated if people put in simple filtering techniques, prefix filtering in the case of route hijacking. So I will enumerate what the best practices are, and I hope that all of you in the room actually follow them. I will talk a little bit about the changing landscape of network level security, and then go into a little bit more detail about IPsec, which I think will be a good benefit in terms of stopping a lot of the current denial of service attacks that are happening today. So what are the major security goals, right? I mean, it's controlling data or network access, preventing intrusions, responding to incidences, ensuring network availability, and protecting information in transit. Everybody's network looks something like this in some way, shape, or form. You've got a core infrastructure. You probably have some branches or other things you connect to. You have a network operating center. And you've got a whole slew of devices that you need to manage and make sure that are accessible and that they actually deliver the data that is meant to be delivered. So risk mitigation versus cost of security. Risk mitigation is the process of selecting appropriate controls to reduce risk to an acceptable level. Right? The level of acceptable risk is determined by comparing the risk of a security hole exposure to the cost of implementing and enforcing the security. It doesn't make sense to spend more money on something than the information is worth. And an example I always like to give is I used to have, I still have 5 different email addresses. I used to support a little ISP because I wanted them to, kind of learn about becoming a real ISP. They never encrypted any traffic, and I always sent my password in the clear. Now, I still use that email. Sometimes I used it during conferences, and my friends would always say, you're supposed to be a security expert. How come you're sending your password in the clear? And I said, well, what's the worst thing that can happen? Okay, I know that everything's being read. I know the password's being sent in the clear. If somebody snags the password and tries to break into their mail server, yay, please do. Because the minute that you break into their mail server, maybe then they will actually fix their issues. So I'm not at risk. Okay, so it's the whole thing about doing a valid risk assessment and looking at what you actually do have to protect, not listening to all the marketing guys and putting in all the features that supposedly make you secure, because what does security really mean in your environment? So the services that you have to look at is user authentication and authorization, and data origin authentication. I always make sure that I break out user authentication versus data origin authentication, because in many instances people say, hey, I'm authenticating this or that. Well, really you want to authenticate a device and a user. And so look at technologies that actually enable you to do both. Access control, data integrity, data confidentiality, auditing, logging, and DOS mitigation. So basically all around your infrastructure, you want to provide these kinds of network services at different levels. The next couple of slides are taken out of a survey that I did a few years ago of large global ISPs, basically all the Tier 1 ISPs. It became an RFC in the IETF. I think the number is 4778. And it was basically looking at what are all the security measures that ISPs are using, and then looking at where there's still some issues and why are they doing some things. And usually it was because you still have legacy equipment in place, or the products didn't exist for what they really wanted to do. So these are basically the topics that it was split up into. So if we look at physical device access, right, I mean, you always want to keep equipment in highly restrictive environments. Console access should always be password protected, and you should always authenticate individual users. I still run into environments where people have group authentication. Do not do this, because if there's ever an issue and you need to trace and try and figure out maybe whose password has been compromised, it's much easier to say it's that particular person than a group where you might have 5 or 6 individuals. So avoid using group passwords. For in-band management, I believe and hope that all of you do this. I mean, there's really never any reason to use Telnet anymore unless you have some legacy equipment that only support Telnet. Always do encrypted access. All access is obviously always authenticated, and again, make sure you have a user-based authentication and individual authorization for what somebody is allowed to do on a device. Strict access control via filtering. This is something that people are sometimes not stringent enough on, where, if you allow somebody SNMP access or a specific device, or you allow SSH access, actually put in the specific IP address or the subnet if it's feasible to have access to. And a point that I'll bring out is that it's interesting. A lot of times, these measures that you see here for device in-band management, people use them for V4, no problem. Then they start playing with V6, and they forget that they should do the same thing. Can't even begin to tell you how many Cisco routers I've seen where you have IPv6 enable, but you don't have any of the access control lists for inbound SSH or SNMP or all those other things. So the minute you turn on IPv6, make sure you also, on your network infrastructure devices, also turn on the filtering and access for IPv6 type traffic. Out-of-band management, very similar to in-band, except that you've created a separate network. And I am going to go through these slides a little bit fast. There's a lot of them, but I'm just going to make the points that I need to make, and then later on you'll have them for reference. So don't get too nervous if you don't follow all of it right now. So for the data path, right, filtering and rate limiting are the primary mitigation techniques for any bad behavior on the network. How many of you do BCP 38 or 84? How many? Why don't the others do it? It's a very interesting question. And I will just say that I happen to be Estonian. I happen to have instigated the RIGHT meeting in Tallinn last May, and it coincided with the Estonian cyber attacks. And I had met the man who ran the Estonian CERT a year prior to that at a conference. And so I was privileged enough to actually be at the NOC when most of the attacks happened. And what was interesting was that when I told him, well, you guys defended pretty well. And he's like, so, do you guys do BCP 38? He's like, of course. And I'm like, there is no of course, that's great. But he's like, but of course, that's best current practice. So it's for those of you in the front, I saw maybe 10 people raise their hands that they actually implement BCP38, which is, filtering, okay, ingress filtering. So I would very strongly encourage you to do that because it stops a lot of stupid traffic from traversing the internet. Okay, routing control plane. MD5 authentication is used to actually authenticate peers who exchange routing information. Most large ISPs do this. The issue has been in key rollover. I've always wondered why IPsec isn't used because if you do know the standard quite a bit, you do get some semblance of key rollover automatically when lifetimes expire. But, of course, IPsec is difficult to configure, and I'll get into why. It doesn't need to be. That's a vendor issue. But anyway, you do want to authenticate your peers if you're exchanging routing information. And this is extremely critical for BGP, really, because since BGP runs on TCP, right, a couple of years ago there was a huge panic where everybody, all the router vendors said definitely use MD5 authentication, but nobody told you why. Well, that was because, you could send a reset packet, and that would actually reset your BGP sessions, causing all kinds of interesting routing issues for a while. So most people then started paying attention and actually configure this. You also want to route limit what routes are believed from a valid peer, and usually packet filters are used to limit which systems can appear as a valid peer. Route filters are really important. They will help alleviate issues with route hijacking. And I'm not going to go into this in too much detail, but if you're not using any type of route filtering, please look into it. Software upgrade and integrity. I was just following the NANOG list. It's the North American Network Operators Group list. And there was an announcement that, what is today, the 20th? The 21st and 22nd, there's a CAN West, some security conference, and some security researcher is going to actually announce a rootkit for iOS. Well, there's been a lot of is this just, is this real, is it not real? And most of the conversation has bandied about that, if you actually do MD5 checksums on your routing images and keep track of if there's anything changed in your configuration files. Using tools like Rancid, that some of these things that people are talking about in terms of installing rootkits and, may not actually work. So good practices, right, always alleviate a lot of the things that you hear out there in the security world where people kind of cause you to panic. So how many of you are familiar with black hole routing? Okay, so I'll kind of go through this just real quick. So a few years ago, I guess 5-6 years ago now, a couple of folks from UUNet came out with this technique, which if you have thousands of routers, it will greatly help provide filtering across your entire network by using BGP to propagate the filtering information. So essentially, you've got a network that has eBGP sessions as well as internal BGP sessions. And destination-based remotely triggered black hole routing, the first thing you do is you identify a trigger router, and the trigger router on the right-hand side here of the slide is configured to redistribute static into every iBGP peer. Also, you've got your provider edge routers. They're configured with static route to unused space set to null 0. When you actually detect that there's an attack, okay, you have to somehow become aware of this. At the trigger router, then you add a static route which sets the next hop to the target destination. This causes the BGP routing infrastructure to propagate the information as to what to filter off your provider edge routers. And then once the attack has diminished, then you basically manually remove the static route from the trigger router, and again, BGP will propagate that information, and installs a new valid route to the target. The problem with destination-based black hole routing is that even legitimate traffic will get dropped. So source-based remote-triggered black hole routing adds a finer level of granularity. So you have the ability to drop packets at the network edge based on the source address of where you believe the attack is coming from. And it permits legitimate traffic from reaching the target destination. It depends on unicast reverse path forwarding, and the packets are dropped if the router has no entry for the source IP address, and if the source IP address entry points to null zero. So this is a slide how that works, and I won't go over that in detail. But on the left, the sentences in blue basically point out what's the difference in terms of using source-based remote-triggered black hole routing. So here's a configuration example for those of you that may not be using it and maybe want to play with it. And this configuration is based on the Cisco router config. And additional things to look out for is you want to be very careful when you're using this, because you want to avoid intentionally or unintentionally dropping legitimate traffic. You also want to keep deploying BGP security features such as neighbor authentication, prefix filters, and the TTL hack, which basically is making sure that you're only one hop away. You also want to use prefix filters at the edge and trigger routes to ensure essential services such as DNS are not black holed by mistake. So that was kind of a really quick synopsis of what everybody should be doing, and I hope they are doing, and I know that you guys aren't doing all of it. So, it's hard running a network these days. But the simple practices really will go a long way to helping stop a lot of these attacks that are happening on the network. Peer-to-peer network is really interesting, right? I mean, users love it, right? I mean, I started using Skype a lot, especially in the last few months, for various reasons. And then also you've got the mobile environments, right, where you can, I got an iPhone. I love my iPhone. I love being able to go to different countries, especially now that I can turn off the edge network and just use a wireless and won't get dinged by, large costs. But it's great. Now, the issue comes in is that what do you do at a network level, right? I love at the IETF, like all these conversations where people are talking about peer-to-peer networking. And there was a discussion where I was like, this isn't really happening, is it? An Apple person, right, was sending in saying that, we have to create mechanisms to automatically create pinholes through the firewall. And I'm like, you what? And they have to do this because otherwise users are going to complain because, they want their traffic to work. And so in the standards bodies, there's some proprietary solutions from Microsoft with UPnP and, Apple does their thing. But they're actually putting wording into the standards how to create, automated pinholes through firewalls. Me, as somebody that's kind of thinking in the security realm, starts to panic. I'm like, okay, this is not good, but what do you do? So you have to look at, what mitigation techniques can you really deal with on the network level. And, for the last 10 years, there have been so many arguments about, well, should security be at the network, should it be at the host? Well, it has to be at both. But let's be clear, the hosts have to become much more involved in security issues. And so at a network infrastructure level, right, you have to do the best you can, but then also look at what can the hosts do to actually have added protection. So IPv6 is kind of interesting because IPv6, right, when people started talking about it 10, 12 years ago, it was an end-to-end solution. So, look at peer-to-peer networks, right? So in a way, I look at IPv6 as they want to create peer-to-peer networks. And a lot of people do want to do that. So who has the control? Well, imagine a scenario, right? what kind of attacks would not exist at all if all packets were authenticated and integrity protected? You know, most of the attacks today, right, there's reconnaissance that happens. And, I mean, I set up an FTP server just for friends of mine. We went on a ski trip. They're not really network people. And I'm like, I've got a server. I'll just set it up for you. Now, it's a 2003 Windows server. I have nothing on there. I have a test lab at home. And I decided if anybody broke into it, I don't really care because there's nothing on there but pictures. And none that I look bad in, you know, so I don't care. However, you know, it was interesting because I monitored really tightly. You know, I have a router, I have filters where I only allow access to that FTP port, one or two other things because I want to monitor it, and I want to monitor it when I'm traveling remotely, anywhere I am in the globe. And it was interesting to me. It was amazing once I started watching how many people just started hammering, trying to get into that server. You know, and I knew the problem was bad. I knew the problem was really bad. It's even worse than really bad, right? Because I only have 6, 7 machines at home. And, I mean, I have it so locked down that, you know, it's really hard for anybody to do anything. Yet they still try. And I would imagine if they try hard enough, they'll probably, you know, there's some new technique and they'll get by. And so what are we going to do about this? And I started thinking about it, and I've been thinking about IPsec for a very long time, and I really am wondering why people, you know, aren't using it as much as I think maybe they could. And in the last 6 years, talking to various people, going to standards bodies and all that, it's become clear to me that users are not willing to pay vendors to actually, you know, improve the situation. And vendors aren't hearing from users that this is a problem and people want to use IPsec more. So to me, it's a chicken and an egg problem. And I will, there's way too many slides for like 5 minutes, but I will at least point out the significant problems. And the packet headers and things that I have in here you can kind of use to maybe think about this on your own. So why do you want to use IPsec? There are so many conferences I go to and they say, you know, we can't use IPsec because then we can't use any of our network level defenses. That is absolutely wrong because IPsec does not mandate encryption. Okay? IPsec can only be used for integrity protection, which I think is a really big win. You can do data integrity and source authentication by using either AH or with ESP, using ESP null protocol. It gives you anti-replay protection and also key management with the IKE protocol. There's a version 1 and version 2, and for mobility environments, there's MobiKE. So, of course, there's always considerations for using IPsec. Now, this is a slide where I just show that, you know, imagine that if somebody's initiating a scan, but you have IPsec integrity protection between different hosts, the scans will not work. Okay, basically, if I'm doing a port scan and wanted to see whether or not a machine has port 21 open, if it's integrity protected between specific hosts using IPsec, the random attacker will not get any information back. And this is huge. I mean, just think about it for a while. Think about if it makes sense. But I've been socializing this for the last 6 months, and it's actually pretty interesting to people. So this is just how IPsec processing works, inbound and outbound. And essentially, if you're not a trusted individual, then the packet gets dropped. So you definitely need to dispel the myth that IPsec mandates encryption. There's 2 modes, transport and tunnel. The difference is that in transport mode, if I am initiating communication, then I will actually use IPsec. Whereas if I am in transport tunnel mode, I am acting on behalf of some other entity. So these are just packets formats for AH and ESP. AH is the authentication header. ESP is the encapsulating security payload. ESP was designed to do the encryption part. AH was the piece that was supposed to do integrity protection. But as it turns out, just historically, people wanted to deprecate AH. Using ESP null gives you integrity protection. The only difference is that you don't have any integrity in the IP header. but it's okay because some of the fields that are mutable aren't protected anyway, and really using ESP null is sufficient. So use these slides just as reference, but I'm going to give a couple of points that I want to make. Why IPsec is problematic is that in terms of IPv6, there's some modifications that need to be made to take into consideration stateless auto-configuration. Because when people created the IKE standard, they didn't take into account that the router can actually send a prefix and the node can then create its own address. So there's a draft for that. You also need to be able to differentiate between encrypted versus integrity-protected traffic. And this is the big point. So if you look at the ESP header format, basically, if you look at the beginning, you can't tell whether or not ESP is being used for encryption or integrity validation. You have to go all the way to the end of the entire packet, which will then tell you that. So that's problematic in hardware, right? Because most hardware only looks at the first X number of bytes. So you can't even tell whether or not, you're integrity protected or not. And even worse than that, you can't even tell whether or not next header is TCP or UDP. So again, this is something that the IETF is working on to figure out how you can easily differentiate whether or not an ESP packet is encrypted or just integrity protected. I'm not going to go through how IPsec works. I'm going to get to the basic points, what need to be fixed. So vendor-specific deployment issues is there's a lack of interoperable defaults. And since '97, when I was still working at Cisco at the time, I pointed out that this is ridiculous, all these IPsec devices, and I started playing with them and doing interoperability. I had to configure every one of them for these stupid, ridiculous defaults, right? Why aren't they all the same? And these engineers would tell me, well, we don't want to mandate a security policy. And I'm like, they're defaults. It's like a routing timer to me. Out of the box, it should meet the requirements of 80, hopefully 90% of the people. And if you don't like the algorithms, then you can modify them anyway, right? Then you configure it. So this is a huge issue. And when it comes to IPv6, we have a small window of opportunity to request that the vendors get on the bandwagon and do the right thing. With IPv4, it's too late because you already have too much of an installed base. With IPv6, because people haven't deployed it yet enough, almost not at all, we still have a small window of opportunity to get vendors to have consistent defaults. So default issue, you look at different vendors, they all have different settings. It's wonderful. Terminology also. I don't know, vendors create their own terminology. So IKE Phase 1 SA in one vendor's equipment means IKE SA, means ISAK and PSA, equates to main mode. They all configure the same thing. Okay, yay. DH, Diffie-Hellman key length, right? So in one vendor, it says Diffie-Hellman group, another one says mod P, the other one group number. Again, same thing. So to me, this is ridiculous, right? And why is IPsec so complex? It's because you don't have interoperable defaults and the terminology stinks. So you could have potentially easy configuration. There's no reason that you can't have configurations like this. Absolutely none. And this would make it as easy to configure, let's say, for BGP pure authentication, it's as easy as MD5. So here's just an example for some configuration examples. And as a summary, use security measures that make operational sense. Sanity filters will greatly stop garbage from traversing the global internet. I mean, filtering really is important. I know it's a pain, but BCP38 or 84 if you're multi-homed, about 10 lines of code. So unless you have a software bug where you can't apply filters to an interface, please use filters. Sophisticated attacks usually start with low-level reconnaissance. So implement the rudimentary security controls, and useful technology can be doomed if hard to use. And it's up to us users to actually go back to the vendors and say, we need this, please fix the configurations. So I'm sorry I went through some of that really quickly, but most of the slides that I just kind of clicked through are really for your reference. And I'll be here for the rest of the week, too, if you want to have any specific conversations. So do I have time for one question? A question anywhere?
Hello, my name is Wolfgang Hinnerbichler from Akunet. I just want to say that you're completely right in saying that IPsec is too complex. I did various implementations with IPsec on open source. I use OpenBSD and Linux, and the main problem there is that you really don't find much documentation. I did some documentation work by myself and put it online and stuff like that. I have many hits on my homepage for people seeking for information. And this is, especially on open source, this is a real big problem. Like OpenBSD has a great implementation of IPsec, but you don't get any information how to configure transport mode anywhere. So.
Yeah, and just FYI, I'm a huge bigot for transport mode, and actually require that for a lot of testing, especially what's going on with IPv6 and IPsec. But in case you guys don't know about this, there's a great website, vpnc.org, run by Paul Hoffman, and it has probably now about 30 or 32 configuration examples from all kinds of vendors and different products from vendors. And it's in tunnel mode, unfortunately, but
tunnel mode usually is greatly supported. You read a lot about tunnel mode, but transport mode is something that also happens and you need to have.
Yeah, if you want to talk offline, because I am creating some documentation.
All right, thank you.
So, thank you.
Okay, our next speaker is Wolfgang John, who's a PhD student at Chalmers University in Sweden. And he's going to give a bit more detail on what some of that bad traffic that's hitting Marika's FTP server is.
Okay, hello, my name is Wolfgang John. I'm from Chalmers University of Technology, which is in Gothenburg, Sweden, and I did this work together with my co-supervisor, Thomas Olofsson. So the presentation is titled Detection of Malicious Traffic on Backbone Links via Packet Header Analysis. So the background is essentially that we have this measurement project where we measured quite a lot of packet level traces on backbone links. And we thought it would be, after doing some other stuff on this data, nice to just look at packet headers and see what kind of inconsistencies and malicious traffic we would find there, just to take advantage of the fact that we have rather rare backbone traffic. So why is this interesting? Well, a lot of traffic filtering is typically done on a local level, and we believe that the backbone data we have available provides a broader view, which can, for example, show how distributed attacks are happening, which is not always obvious on a local level. Then we were interested, well, are there some old, well-known attacks, are they still out there? And on a larger view, you have more chance to find those very rare events. And essentially, we asked the question, what can you expect to happen on backbones, which will eventually show up at some ingress hosts? And it's also boiling down to the question, how good is really just pure packet header analysis? There's not much correlation between the packets we do in this study. So the outline of the talk will be that I start to talk about the packet headers we consider. So we have a rather specification-based approach, which means we take packet headers, look at the fields, which of the packet fields would be interesting and security relevant. Then we apply this on our data set. We search through all the packets, all the packet headers, and try to find how frequent do these errors happen. In this regard, I want to then introduce also the data set, that you get a feeling of which type of data we are talking about. And then finally, number 3 is the most important part of this talk, about the anomalies observed. And I will not have time to go through all the details, but I want to highlight some stuff we found. And then I will just summarize and conclude the talk. So the packet headers we consider are IP, TCP, UDP, and ICMP. And on these slides, you see everything in gray is headers, is packet fields we considered, and white we did not consider for this analysis. And the Roman numbers will be used later on to identify the type of attack. So we tried to have our own small classification, which should be used if you read the article like an index to later chapters if you are interested in some specific fields. So this is the IP header, where for TCP it's a little bit less complete. For example, we did not consider the sequence number, even though I know there are some interesting stuff to look at sequence number level as well, but there's quite some limited scope, so we cannot go into all the details. And we also left out receive window and checksum, obviously. UDP header, we checked pretty much everything except checksum. And concerning ICMP header, it would have been very interesting to see to take a look at the payload of the ICMP headers, which is typically IP packets, or the packets which initialize this ICMP header in reverse, but unfortunately packet payload was removed in our data, so we just give more or less a survey of which types and which codes would you see out there in real traffic. So that's pretty much what we were searching for. And now to our data set, that you know in which kind of type of data we were doing this. So this is a very simplified picture of where we are located. We are sitting here in Gothenburg. And at this time when we measured, the Swedish University network had the local internet exchange port here in Stockholm. This should be a ring architecture, where from our point of view, almost all traffic is routed via this link, and this is more or less a backup link. And the type of traffic we would see on this link is everything from two major universities and some smaller universities and institutes, a very large student network in the whole region of Western Sweden, and some exchange traffic with regional ISPs, so commercial traffic as well, which is all passing to and from the main internet via this link. And that's also where we were measuring. So these are two 10 gigabit links, one for each direction, where we used N-day stack cards to capture. For privacy issues, we were allowed to capture headers only. IP addresses had further to be anonymized, so those two facts limit our analysis possibilities in some ways, but we did what we can. And the data we were looking at is 554 traces, where each trace consists just of a 10 minutes interval, because we don't have the capacity to capture continuously. And we did this during 3 months in late 2006. And as a summary, we ended up with about 28 billion IPv4 packets. You also see here the traffic breakdown, where basically it's 90% TCP traffic, some UDP traffic, and very few other type of traffic. If you're interested into more details about the traffic, just Google .cat and SUNET data, and you will get a very good description in Kaida's .cat. It's the data catalog by Kaida in the US. So there's a very detailed description of the procedure, how we collected the data, and which type of data it is. In this slide, I also included fragments and fragment series we saw. So I think people typically know what IP fragments are. So if you have an original datagram, which is too large for the next transmission unit, for the data link network you're working on, so you just divide it, you take slightly modified copies of your IP header, and then you got your fragments, which are counted as IP fragments. But the more important thing is, what do we really mean by fragment series? And a fragment series is, in our sense, defined by a series of fragments belonging to the same original datagram. So that's the only correlation we did in this data, because we believe that fragmentation kind of attacks exploiting different fragmentation are a rather important class of attacks. So we felt that this is necessary to look at. So let's move on to the anomalies we really observed. So in the following slides, you will see a couple of tables, and I try to walk you through these tables. But I will not go into all details, so feel free to look at the Terina webpage you don't only have the presentation, there's also an article about this where you can find a lot of details. So here are the IP header anomalies we looked at, where again the Roman numbers refer back and forth to the IP headers. And you have the number of packets we counted for this event. For IP, we also divided it on transport layer, and it has the description of what it really means. The first three are very general IP header problems where IP version fields are misused, IP header length and stuff like that, usually happening in combination, but very rare events. I mean, you need to consider that these packets are out of 28 billion, so it's too small numbers to give relative fractions, we felt, so we give you the absolute numbers here. The next attack would be where you have source IP address equals to destination IP address, which was typically the LAN attack. But the LAN attack used TCP SYN packets, which we just see 9 of them. So we rather believe that what we see here, these UDP packets, are either misconfigurations or hardware, software errors, something like this, than attacks, because it's also quite randomly there's a lot of different hosts involved at different times, so maybe it's a modified form of the LAN attack. It's a little bit unclear. Then we looked at the reserved address space, where you see quite a lot of packets, more than 2 million. And this number is very large because there are 2 outstanding events, so 2 intervals where about 1 million packets were sent just to 4 addresses, so this was a very directed attack. And the source IP address of class C network was used. So to make this clear, the reserved address space we look here at is class A, B, and C private network space, plus loopback and class E networks, I believe. So all those packets we saw here in those 2 campaigns were basically SNMP echo replies with consistent length. So this is very, very, very likely to be a kind of denial of service attack or some kind of attack. So we also looked at invalid usage of IP flags, where you typically have packets which have more fragment and don't fragment bit at the same time, which should not really be there. We tried to get some useful information out of small TTL values, which is tricky because, for example, traceroute would use this as a valid way. So this was kind of hard to analyze, but we did our best, and you can find some details in the article as well. And then we looked at IP options, which are in some sense also sometimes used for security-related issues. For example, the good news is that we didn't find any use of the IP source route option, which was used for different types of attacks in the past. So that's probably the good news here. So let's move on to IP fragmentation inconsistencies. Excuse me. So you need to be careful now here because these counts are now about fragment series. So the reference number is here just about 20 million. So this is very large numbers already in comparison. So the first thing we found was in general that IP ID values of 0 are clearly overrepresented within all these numbers. So we are not sure about this yet, but it might be some indication that you can use this for identifying attacks maybe. The first thing we found was a kind of exceptional event, which includes a lot of fragment series, where it was a single host at the university involved in this campaign, which showed just up in 5 intervals we measured, each interval to different destinations, but with very similar patterns. You had fragment series consisting of about 6 to 7 fragments, and as destination port, it was iterating over the whole port range. And half of all those series, so there were in total like 3 million series seen, and half of them, which is this 1.6 million, had some inconsistency, usually gaps and holes and overlaps and all kinds of stuff. So we believe that this is probably a hijacked host by someone. It could be someone in the university, but we rather like to believe that it was hijacked and is a denial of service attack to some, or distributed denial of service attack to some directed attack to some hosts. So these numbers are then not included into the following numbers where we look at the remaining occurrences. We tried to look at series with short first fragments. I don't want to go into detail here. We have some single packet series, which are in fact no series because it's just a single packet, but there is either the more fragment bit set or there's an offset set, so they're supposed to be in a fragmented series, but you never saw the rest of it, which could partly be caused by packet drops, but also to more or less confuse the receiver. So he needs to keep this packet in his buffer and is waiting for the additional fragment, which will never show up. And that's also the case for the incomplete series, where you just have in between some gaps, and since the fragment, so the original datagram can never be reassembled, it's quite unnice for the receiver. And for this 30 million packets series of fragments, there were just 42 hosts as the main target, so very limited number, so again a quite directed attack. And out of all these fragment series to these 42 hosts, 1/5 had those gaps. And there were many gaps which were very short, just 8 bytes, so that's very unlikely that they were actually supposed to be, because usually you would send full-sized packets and then in the end the remainder, which could be shorter. But if you have a gap in between, which is rather short in a fragment series, that's very unusual behavior. And since 1/5 is also quite a lot, it seems to be unlikely to be explained by pure packet drops. So we believe that what we see here is, again, denial of service attacks. Then you have some overlapping fragments where we saw very few of them, but those very few of them interestingly showed up at a completely different time between different hosts, but they have very similar patterns. So they don't just have gaps, they also have, don't just have the overlaps, they also have gaps in exactly the same size, just that these gaps are filled at the wrong places. And since it's such a common pattern between different hosts, we believe that either this is a hardware or software error of some common tool, or it's a kind of common attack tool which is forging you this kind of packets, this kind of attack. Then we have duplicate fragments, which is kind of a special case of overlaps, just that it's exactly the same fragment which is overwritten, which is, many of them can be explained by retransmission, so that's not really security relevant. And then kind of the good news, we also looked at how many of the series would exceed the maximum IP datagram length, which was formerly a quite popular attack known as ping of death and other variations, and this was not observed at all, so that's some good news. At least not in the traffic we looked at. So let's move on to DCP anomalies, where in the first row we binned completely garbled DCP headers, where what we defined as 2 or more more independent field anomalies within the DCP header, which means typically these headers were just random bits. So there's not so much to really analyze about them, except that they exist. So those numbers are then removed from the remaining columns. So we looked at DCP length fields which are too short to be true. We saw quite some usage of the reserved bits, which are the bits before the signaling flags, which should be 0 according to the standards. And those 150,000 DCP packets doing this were to 1/5 of them. They were in reset packets coming back from web servers. And since we saw valid transactions going on earlier, we believe that this is just a strange type of web server who's doing this for some reason, but it's not really a security issue. Whereas the remaining 80% were seen in SYNAC packets only, and those SYNACs were consistently not triggered by any SYN packets. So, of course, you could explain maybe some of them with asymmetrical traffic, but since we didn't see a SYN packet for any of them, it's very, very likely that this is a SYNAC attack, which for some reason happened to have the reserved bit set. We looked at TCP port numbers of 0, which was equally between source and destination port numbers of 0. And this was very easy to verify that these are typically SYN packets in host scanning campaigns. So if you looked what happened before and after these packets, you would find those board sweeps or scans. We also looked at all combinations of invalid signaling flags, where you should rather read the article. I will not go into detail here. And this just confirms the number we got from previous studies where we did something similar with these reset packets. But this time we also looked at pure FIN packets, so FIN, where the FIN flag is set but no acknowledgement is used. And there was a related work which suggests that this is quite useful to reveal board sweeps, but we didn't find this supported by our data at all. So what we found rather is that those pure FIN packets are going to peer-to-peer boards after a series of SYN connection attempts, which looks like quite valid. So I rather believe that this is a bug in some peer-to-peer applications, or a strange behavior, but it's not a major concern. We looked at a number of other things, including how many urgent pointers are used, obviously quite few, and very few of them seem to be suspicious to be used for malicious activity. Let's move on to the UDP header section, where we found a few packets with UDP length fields which were not sufficient to host a full UDP header. But here we also found quite a large number of UDP ports of 0 used. And in this case, it was typically source port numbers. And there was a quite interesting pattern when looking at these UDP ports of all the packets using UDP ports of 0, since typically we saw from one host exactly 508 packets. And that was because they scanned over /24 network ranges, which would mean 254 IP addresses. And doing this, all of them did this exactly for 2 port numbers, which you end up with 508. So this is quite a nice evidence of Windows messenger span. Using UDP to these RPC ports on Windows and just scanning over whole IP ranges. Finally, we looked at the ICNMP headers, where we basically surveyed occurrences of the ICNMP types, plus how many undefined types and how many length violations we would see. And I don't want to go into detail here too much. I just want to point out that like 50% of the ICNMP packets in this time when we measured were redirects. And that's actually just coming from 2 hosts, sending about 46 million host redirects during an interval of 2 days. So all the 10 minutes intervals we measured in the 2 days, they were always on. And in the rest of the time, those 2 hosts, which are in the student network, were doing some web surfing and peer-to-peer applications. So probably there were some students who thought it would be funny to launch a kind of denial of service attack, or they were again hijacked and didn't even know about this. And there are well-known attacks using host redirects to mess up the routing information in some hosts. To give a summary about other security-related ICNMP header observations, well, as mentioned before, there were no ping of death type attacks, which is the good news. We didn't find any obvious attack patterns using the destination unreachable ICNMP messages. We saw no obvious attacks of ICNMP timestamp attacks, and well, there's this kind of attacks where you would just forge random ICNMP packets and hammer it to one host, which we didn't see. So those invalid packets we saw were spread out randomly over all intervals between different hosts every now and then. So this means that I want to summarize and conclude this whole talk. What do we think we really found? Basically, I think we provided a nice systematic listing of header anomalies according to our definition. So it's a very specification-based approach. We took the headers and then digged through all the data. How much invalid headers would we find in real data? And then we presented these occurrences in this data and tried to discuss the reasons for it as good as we can. So the high-level conclusion would be that many of these old, well-known attacks are still out there. Sometimes in very small numbers, but they are there. The good news is that some of these formerly popular attacks have vanished. No ping of death, no IP source route routing used. In general, I didn't mention this too much because I just highlighted now the big outstanding events. But all the other numbers you saw were like a constant background noise of anomalous packets, which just happened between a lot of different hosts during all the time. So they are just there, and a lot of them are probably also by software, hardware failures. So that just some bits flipped every now and then. Some of them, or a large number of them, is probably also explained by tools like Nmap, where you can easily create your own random packet as you want. And since these tools are very easily available now, and even a very inexperienced user can do it, I think this explains why you see those weird packets out in the network, even if they shouldn't be there. And as I highlighted in the talk, there were some major campaigns of malicious activity detected. And so the pure packet head analysis reveals quite a substantial amount of malicious activity, as you saw in the numbers. And what was quite nice is that very often we could identify attacks by looking at complete, like, secondary signs of this. So we looked for example, you look at the reserved bits and you find denial of service attack. So it shows that it's worth it to watch at least out for those fields I mentioned here, because they turned out to be the most efficient to identify attacks. So the ID of 0, where we want to look a little bit more into it, but port numbers of 0 were very effective to identify scanning campaigns. Strange TCP flags, but that's well known, the Christmas attack, Christmas packets type. Reserved IP addresses is a very obvious rule you should have in firewalls, because they're just around there and usually not behaving very nicely. And then ICMP activity should be monitored as well. So what's the next step after this study? Well, as I mentioned, there are some additional fields or things we would like to look a little bit closer to. Then it would, of course, be very interesting to get some access to payload data, or, for example, also to real IP address data, not anonymized, because then it would be able to look also at broadcast addresses, which I think is a very popular type of attack, to misuse broadcast addresses. So there's a lot of stuff to do in this concern. And then, of course, it would be interesting to further correlate the packets. For this study, we just correlated packets for this fragment series. But of course, if you would combine the approach we did with a flow analysis, you would see much more scanning and denial of service attacks and port sweeps and whatever. And also, it would be very interesting to see what happens before those attacks, scannings, whatever you see, what happens before, what happens after. But, well, that's future work. So if you're interested in more information about the data or the measurement studies, feel free to visit my webpage or send an email. I'm glad to take up any type of comments and questions.
Thank you very much. There's already a question at the back.
Hello. It's rather not a question, it's a comment, because you said something about IP options. I know that there was a bug in the early version of Linux 2.6, which goes to, with the, of course, the invalid options set in the packet, which goes to infinitive loop. So probably those are the, maybe not exploits, but some kind of packets which goes to put the firewall based on Linux into the infinitive loop, which goes to the DOS attack efficiently. So that's basically why you observe so many of them. It was up to 2.6, probably 12 or something like that. There was a patch for that.
Thanks for this comment.
Okay.
And our third speaker this morning is Maurizio Molina from Dante, who's in their network monitoring and security group, and he's going to come up with some more suggestions on how we can deal with these things, I hope.
Okay, thank you very much. My name is Maurizio Molina. I work for Dante. For those who don't know that, Dante is the operator of the GEAN2 network, which is the European backbone for the NRENs, the National Research and Educational Networks. At the IP layer, it consists of roughly 20 routers spread in the European countries. Today I'm going to talk about a network security service for the GEAN2 network. And I'll first go through the vision that we have for setting up and delivering this service. I'll talk about the preliminary step we took in order to see whether we can actually do what we want. And then I'll talk about the talks we made about the tools that we need to support such a service. And then I'll wrap up with entering into a bit more details about what the specific service elements are. So let me start with what the situation is. The current situation is that NRENs have their CERTs, so their teams dealing with security incidents, and of course they are already collaborating with each other. For example, in Europe there is this Trusted Introducer initiative, which is basically a way for CERTs to share information about security incidents in a trusted and secure way. There is an initiative within the GEAN2 project which is called GRA2. It's a research initiative for developing and enhancing tools for network security and anomaly detection and improving the communication between NRENs. Dante, that is my organization, is there, and we can filter out traffic at the backbone level if NRENs request us to do so. But the missing bit in that all is that we would like to bring into the picture the visibility that we have of the core and be more proactive to NREN search, so signal them about anomalies and security incidents that we can spot with our visibility of the backbone data. So this is a challenging task. Of course, we need to use data to do that job. What data? Well, S&P is, as you may understand, useful for network management, but for dealing with security incidents, it's two cores, both on the time granularity and on the space granularity. Knowing how many bits and bytes transit through an interface of a router in a given time interval is not enough. Router logs is a technique that has been and is successfully used for dealing with security hazards. The main problem is that you have to have a very deep understanding of your network in order to set up the useful logging filters that you need. So in a way, you need a lot of a priori information for using this technique. Running a darknet that is listening on an unassigned portion of your address space and looking at who's trying to communicate with this address space that should not be used is also a technique which is widely used. We could do that, but well, our network is a /19, so it's not particularly big in terms of addresses that we could devote to such an activity. And so it's not where sitting on a backbone network handling tens of gigabit per second of traffic is making a difference. So the obvious choice for the data on which to deliver such a service would be NetFlow, which I assume most of you know what it is about. Is information about the amount of traffic or flows exchanged between end hosts. So, for example, TCP connection is an IP flow. This information is exported by the routers, and it can be used successfully for detecting security incidents, provided you have the right tools. Routing data is also something that we want to bring into the picture, mainly as a complement of NetFlow data. So, being NetFlow the primary source of information we want to rely on, what is the current situation? The current situation is that on our 20 or so routers, we collect net flow data in all the interfaces peering with an external peer. These external peers are, of course, all the European NRENs, and they are also peers that are not our customers. For example, the American equivalent, that is the Abilin network, or the Chinese equivalent, the Japanese equivalent, so the research network there. We also have some gateways for global IP connectivity with two global providers, TILIA and Global Clustering, and these are peers as well, so we would collect on these peering interfaces as well. Currently, we are using one-to-one sound sampling, and this boils down to producing 3 kiloflows per second, which is not an incredible amount. We collect this information, and we are using NFSen, which is an open source tool developed by Switch, the Swiss NREN, for processing this data, enhanced with some self-written anomaly detection extension that I'll show you in a few moments. So the first question to answer is, what statistic generated by NetFlow do we want to rely on? NetFlow can give you information about bytes per second, the packets per second, and the flow per second. Now, flow per second proves to be the most useful statistic for detecting security incidents because a lot of suspicious and malicious activity use small packets, so this would not be recognized if we focus just on the byte per second statistic. But even focusing on the flow per second, a first problem immediately comes in mind, which is we cannot just rely on fixing a fixed threshold and try to see when these statistics overcome this threshold, because in the traffic we observe there are a lot of daily and weekly cycles. So if we fix the threshold simply to capture the bigger peaks, we would leave the smaller peaks unobserved, and more frequently these peaks are related to security incidents, possibly impacting the service on some end customers. So what can we do? The obvious idea to overcome this problem is to try to focus on the variation from a baseline. Okay, so I had this idea taken from the automatic control theory to build a simple filter which is called an observer that takes the current reading of the statistic, for example the flow per second, and tries, thanks to these two discrete integrators, to make a prediction of the next reading in the next time slot. And the difference between the actual reading in the next time slot and the prediction is called the forecast error. Now, in control systems, it would be used to control actually the system, and we would use this forecast error in a feedback loop. In our case, we just use it as an indication that something very different is happening in the current time slot with respect to what it was in the recent past. The equations governing the system are very simple. They are written here, and only the tuning of these two parameters is required, which is pretty simple if you have some hands-on on this system. So this is what happens if I apply this methodology of filtering through this observer on the same, let's say, on the same statistic I've shown you before. Well, you can see that at least for UDP flows, we start seeing something. So we have eliminated the continuous component, and some peaks are evident. But for TCP traffic, for example, the situation is not clear at all. And TCP, of course, is the predominant protocol using the network. So I'm not still happy at this stage. So how to go on? I looked at recent work in the anomaly detection literature and find out that more and more people were focusing on suggesting on a methodology called IP feature entropies. That means focusing on the concentration or dispersions of 4 features that are the one listed here. The flows per IP source address, the flows per IP destination address, the flows per IP source port, and the flows per IP destination port. In this slide, I'm showing visually what an IP feature entropy means. Suppose, for example, that you concentrate on the destination IP address, and in a certain time slot, for example, in 5 minutes, you rank your receivers of IP traffic on the basis of the number of flows they receive. And so you build an histogram like this. Then you do the same thing in a different time interval, for example, in the next 5 minute slot. If something happened, if something, let's say, not normal happened in the second time interval, for example, if traffic was more focused towards a few set of hosts, then the histogram would change. So the distribution would change, and it would become more skewed, more concentrated toward a limited set of receivers. Now, the entropy is simply a mathematical transformation that allows you to capture with a single number if the distribution is concentrated or dispersed. In my implementation, for computational simplicity reasons, I didn't use the actual formula of the entropy. Rather, I simply concentrated on the top n contributors to the distribution and evaluated what their percentage of, for example, of flow per second they were contributing to the total. I empirically tried a few numbers. For example, I tried to concentrate on the first 1 contributor or 10 contributor or 100, 500, and empirically found out that n equal to 10 was the best choice for letting anomalies to appear more evident. And the next graph actually shows the first application of these methodologies, so extracting the IP feature entropy on the 4 features I mentioned you on 10 days of Gentoo traffic. So what you can see now is that we have completely eliminated the continuous components, so there are no more daily and weekly cycle evident, and there are peaks very evident in certain parts, both for the TCP and for the UDP traffic. Of course, the interesting thing starts when you start drilling down on some of these peaks. This is an example for a peak in the TCP time series. Here you see that 2 of the features are going up, and these are relative to the destination IPs and destination ports. 2 of the features, on the contrary, are going down. So because of the type of filtering we do, when it goes up, it means a concentration of the distribution. When it goes down, it means a dispersion. So in this case, we have a concentration of destination IPs receiving traffic and a dispersion of source IPs. Okay, this should ring a bell, shouldn't it? Yes, it is a targeted DDoS attack, and we found out there was an IRC service in Slovenia receiving a lot of 60 bytes SINS packets on the standard IRC port, and the source of these attacks was distributed in a lot of hosts belonging to a single university in the Netherlands. So most likely it was part of a botnet war. Just observe that here, actually, the anomaly just lasts for a few minutes and then it terminates. When it terminates, we have this bounce here. This bounce is not real, so we don't have a dispersion of the distribution here. It's just a consequence of the dynamic of the filter. And the problem is that in order to correctly interpret that, we have to build a state machine, not to be fooled of the fact that we see a bounce after a rise. So we have to take into account with a state machine processing this time series and keeping some memory. I've tried to do that. I've obtained some, let's say, decent results, but I think there is a lot of work to be done for improving this methodology yet. Another example on the UDP time series. Here we have 3 features going up, as you see. So 3 features getting a concentration and 1 feature is going down, so getting a dispersion. The dispersion is on destination ports, in this case, and the concentration is on all the other features. So concentration on destination ports should ring a bell immediately, which is, okay, it may be a scanning. And in fact, by drilling down and analyzing, we identified that it was a port scan in a host in the Croatian NREN, carried out by 4 hosts with 29 bytes packets. Observe again the bounds that we have to eliminate through an intelligent state machine. This is another example, this time not taken on the overall Gianto traffic, but rather on a single NREN access. This is one of the NRENs exploiting our Dante War service for global IP connectivity, so one of the NRENs for which we transit on these global providers that I mentioned before. What appears evident here is that at a certain point in time there was a huge burst of anomalies and indications. This was, of course, suspicious, and so I looked at the total volume of traffic received at the point and find out that due to our rerouting, probably due to one of the router migration we were carrying out in this moment, the traffic was rerouted elsewhere, so we had no traffic there. So the lesson learned by looking at this graph is that you can't just focus on the IP traffic features. You always have to also to couple it with the volume observation of the traffic flowing into your network in order not to be fooled by false alarms. Other than that, if we do that, so if we eliminated this false alarm here, you see peaks are very evident on this baseline. And these peaks may be related to network anomalies and security incidents. Another graph relative to an NREN which is not a Dante War service customers. Once again, peaks are quite evident, although there are fewer of them. So, lesson learned so far, by using the IP feature entropies, we can actually spot also low volume anomalies. We need a state machine to interpret this anomaly and to correlate the 4 features between each other. Fully automatic conclusions are still difficult. There is a point in which I have to stop and do some manual investigation with the aid of NFSEN to carry out a final conclusion. And the other lesson learned is that you always need to correlate that with the volume of traffic that is globally entering into the point you're monitoring in order not to derive false indications. A lot of anomalies are observable on the Dante War service connectivity. This is not surprising. A lot of malware is coming and going from the global internet. So this would be a good reason for having such a security service for protecting our Dante War service customers, but we've seen also a lot of attack scans between NRENs as well. Moving forward, we would like to test some commercial tools, so move beyond NFSEN for a number of reasons. In particular, we need to contain the effort to develop and engineer and maintain and evolve code for implementing this methodology. What I've done so far, I regard it as mainly as a proof of concept, but to engineer, to carry it to a level necessary for delivering a real service, there would be an enormous amount of work. Also, the stability and the tool support is an issue for delivering a service in the long run. So we started looking at some commercial tools, and the obvious requirement for this tool derived on the previous observation we made is that they need to detect both high volume and low volume anomalies. they have to be able to do some automatic anomaly classification along the lines I've started to do. They should detect the anomaly entry point and possibly suggest some mitigation actions. And also they should give correct indication also in the presence of sudden traffic changes like the one we saw before. Ideally they should be robust to occasional loss of network record that unfortunately happens, and they should work well also with sample net flow, which is what we are currently doing. We've just started this work, so I just briefly report on what we've learned via some on-paper analysis of 4 tools and interaction with vendors. Out of these 4 tools, we are going to test some of them, a subset of them. First of all, the approaches the tool take can be summarized in these 3 ones. The first one is the IP feature entropy and volume approach, which is the one I showed you before, that has the pros that you don't need any a priori information, but the cons is that the level of conclusion that you can reach is not always complete, so you sometimes need to carry out a manual investigation. Another approach can be to use to focus on volume shift and using fingerprints. You can imagine as a fingerprint as the characteristic of an attack, like the one that were described in detail in the previous presentation. So if we were able to define a priori what we are looking for, we could just raise an alarm when some of the traffic we observe is matching exactly what we expect. This has the advantage of being very precise in the sense that an alert is already a conclusion, but you need to know a priori what you are looking for, and you may risk to miss what you don't expect. Then there is another approach, which is a per host behavioral analysis. So you can, instead of focusing on traffic aggregates, you focus on every single host you see, and you can try to profile it and attribute it to a certain behavioral category. For example, a web server or a mail server or an ordinary client, and try to understand whether the behavior of this host is drifting dramatically from the baseline you have established. This approach is potentially interesting. It has, of course, the issue that in a transit network like ours, we may have scalability problems, and also I'm concerned that it has to be robust to a low sampling rate like the one we have. Most of the tools we saw have common features. They require NetFlow on ingress links only. They are capable of doing both NetFlow v5 and v9, and they require SMP access to the router to read configuration data. The distinguishing features of the tools, on the contrary, are mainly the following one. Some of them are capable of doing some BGP processing, and this is important to create pop-to-pop or even prefix-to-prefix matrices, and this is important to correlate big volume shifts to routing changes. So a tool capable of coupled BGP processing and network processing would not be fooled by an event like the one I showed you before, where there was a sudden drop to zero of the traffic. Some of the tools are capable of processing IGP information, and this is important for having the traffic split on internal backbone links, which is an information that you don't have otherwise. And this is a feature which is particularly important for traffic engineering, not perhaps that important for security reasons. Some tools also can collect NetFlow on multiple points, but I see that as an additional burden rather than a feature, because it means that these tools are not capable of processing routing data. As regards the approaches used by the tool in order to distinguish what is not normal from what is normal, there are these main approaches. The first one is called the principal component analysis, and basically it tries to infer from the previous days or weeks of analysis a daily or a weekly or hourly cycle, and just focus on the variation of the established baseline. The host type classification and scoring system is another approach which pertains to these tools that are trying to profiling each and every host. And then some of the tools I've looked at also use simpler methodologies like moving average and fixed thresholds that are a bit primitive in a certain sense. Okay, that's basically it for the description of the technologies. Now, what's happening next? We are basically now carrying out the testing of these tools, and we are setting up the service. Our primary recipient are the NVEN certs. I want to stress that. So, for example, in a case like the one before, where we identify a DOS attack coming from a university in the Netherlands, we would go to the SurfNet cert, alerting them, and not to the end institution. The info provided in such a service will be security alerts, along with all the evidence that we can collect about it, and the suggested mitigation action if we are good enough, or better, if the tools are good enough to automatically suggest a mitigation action that, by the way, would need to be approved by the NVENs before we implement them into the Gian2 core. We also want to produce some summary reports along the lines of the monthly report that we already produce for the NVENs, for the access point managers, etc., but focus on security events rather than on just traffic, on the traffic like we do currently with our monthly report. And of course, this, in our vision, should be able for these bodies to take strategic decision in the security area. Okay, I'm finished. Let me just thank a few people. First of all, Professor Francesco Donati and Dr. Gabriella Caporaletti from EICAS Automazione, an Italian company, let's say, with a huge reputation in the area of automatic controls. They gave me the initial tips of trying to use this observer thing and helped me in the tuning of its parameters. And then I want to thank Peter Hag from Switch for having developed NFSend, which is the tool that I use for developing my extensions and doing the drill down analysis I showed you. Okay.
Because we've done work based on similar tools, we found out that to correlate various measures, like for instance sin over fin or TCP flows, things of that sort, because it is very tough sometimes to detect within very large volumes of traffic by using just a simple measure. So what we've done, and we still do, is we try to combine measures. And you mentioned, I believe, one of them, and that was the principal components analysis, that it is in a way trying to do that. I would like to ask you if you tried something, since you mentioned this information theory kind of approach, if you tried to look at mutual information, things of that sort.
Mutual information?
Mutual information, yes. I mean, you have two measures and you try to see if you can minimize or maximize the mutual information.
No, not myself.
You mentioned in the entropy analysis that it works fairly well with low-rate sampling. Could you give us some numbers about that? And with what sampling rates did you make it work well?
We use 1 to 1,000 sampling. And in the papers I've seen in the literature, they were considering sampling rates of this magnitude. We may want now to move to higher sampling rate. Now we have migrated the router platform of the Gian2 backbone to a newer architecture, so we are potentially able to go beyond that, the sampling rate. I'm waiting to see what I can see with commercial tools with the current sampling rate before deciding whether to move forward, because increasing the sampling rate is not just putting additional burden on the routers, which is probably not an issue if you have a platform supporting it, but it means producing a lot of data that you have to collect and to process, etc. So scalability becomes an issue with a backbone network like ours.
Thank you very much. Thank you to all of the speakers, especially for keeping very well to time. For anyone who felt that lunch was a little bit congested yesterday, there is also a small number of lunches available in, I think it's the Vives room, which is, I think, a couple of doors down to the left. The main lunch server is upstairs, as before, but there is that overflow if you want to use that. And look forward to seeing you back again this afternoon. Thank you very much.